Welcome to first part of Boolean algebra examples. In the last two presentations, I explained you what is Boolean algebra and what are the different rules involved in it. I explained each and every rule and also proved them. The rules I have written on the right hand side of the screen so that we can use it directly while solving our examples. And the first example is A and B or A and B complement. We have to minimize it by using this set of rules. So let's start. Solution. Let's say this is function f, a and b or a and b complement. If you remember the priority I told you, the not is the highest priority, then and then or. So first we try to implement the De Morgan's law, that is actually the complement law, and we can find that there is no such case like this too. So we cannot implement the De Morgan's law. So this is gone. Then we will see for and if we can implement any of this here, and you can see we do not. So this is also gone. The only thing is left or. So function f is equal to, you can see a is common in both the literals. So I will take a common, and in bracket I'm left with b or b complement, and b or b complement is equal to 1. Here you can see a or a complement is equal to 1, so b or b complement is also 1. And now we have a and 1. A and 1 is equal to a from here. So the function f is equal to a. You cannot minimize it further, so this is our answer. So this function a and b or a and b complement is equal to a simply. So this is equal to a. Now you can prove this by using the truth table. So let's do it quickly. We have two variables a, b. The output is f, and this is equal to a, b or a, b complement. And as there are two variables, we have four possible combinations: 1, 0, 1 or 1. Now let's try to find out the value for f. When a is 0, we have 0 and b is also 0, or 0 and 1. B is 0 and taking its complement we have 1. So overall we have 0 or 0, and 0 or 0 is equal to 0. So function f is equal to 0. Function f is equal to 0. In the same way, if I have a as 0 and b as 1, I'm going to have 0. And when a is 1, b is 0, let's see what we have. A is 1, b is 0. So you can see 1 and 0. 1 and 0 will give me 0. 1 and 1 will give me 1. Or is there, so we have 0 or 1 is 1. I have told you whenever you or anything with 1, the output is always going to be 1. So 0 or 1 is 1. So I have 1 here. In the same way, if I see for the last case, then we have a as 1 and b as 1. So a as 1 and b as 1. This thing is equal to 1. So once you have anything odd with 1, I'm not going to evaluate this thing because it is a and b complement. Whatever be the value of this thing, we have output as 1 because this thing is odd with 1. So the output is 1. Now you can easily compare that a is 0, 0, 1, 1, and f, the function, the output is also 0, 0, 1, 1. They are same. So whatever be the value of b variable, it is not affecting the output. So why to write this whole thing when you can simply write f is equal to a from the truth table also. You can cross check your answer from the truth table, but we are not going to do this thing in the exam every time because we don't have that much time. We will practice lots of problems so that it will prevent us making the mistake. Now let's move to the solution number 2. In this, the function f is equal to a, b or a, b complement c or a, b complement c complement. Now you can clearly see that this a is common in all the three literals. So I will take a common, and in bracket I have b from here, b complement c or b complement c or b complement c complement. Okay, now we have to use this rule that I told you very important one. In this you can see when we have A or A complement B, we have A or B. I just omitted this thing. In the same way, if I compare this two, I will eliminate B complement. So I have A, B or C because I have eliminated B complement by distributive law. This thing is written as it is, B complement, C complement. Let's see what we have in the next step. And again you can see we can implement this law once more. Here if I see B complement, C complement, I'm going to again eliminate this B complement so that I will have B or C complement or C. Now it is really easy to calculate C complement or C. From here you can see A complement or A is equal to 1, so C complement or C is also equal to 1. So B or 1. B or 1 from here you can see is 1, so A and 1. A and 1 from here you can see is equal to A. So this large function is equal to A. So this is the beauty of Boolean algebra. You can reduce this thing to such a small value by using this set of rules. I think this is all for this presentation. We have solved 2 examples, and in the coming presentations we will solve some more examples that will help us build our concept. There is some advantage of minimization. Why we are minimizing? The first advantage is the reduction of hardware. Definitely you are going to use less number of gates, so you are reducing the hardware. The second advantage is minimization in cost. Once you reduce the hardware, it is obvious that you minimize your cost because the hardware is having some cost. The third one is increase in speed and fast response. When you reduce the number of gates, each gate will have its own time. For example, you have 3 components and these 3 components is having its own time. Let's say TA, TB, TC. After TA this will produce the output, after TB this will produce the output, and after TC this will produce the output. So total time is equal to TA plus TB plus TC. Now by some means you eliminate this block and the functionality remains the same. The output is not affected. Then the time will be, let's say it is T dash, the new time, it is equal to TA plus TB. So we can say that T is greater than T dash. So we have reduced the time, and also the power dissipation is reduced.